Okay, so in this video we're going to talk about power series. Now, power series are their own series, and actually they're a pretty important one you see in much higher level math classes pretty commonly. So it's important to recognize when power series converge, and that's what we're going to talk about now. So, first of all, we've looked at series of numbers so far. That is, basically like 1, 5, 1/3, etc. Things that are actual numbers. But now we're going to be looking at power series in which each term includes a power of the variable x. So something like this would look like 1 x, x squared, x cubed, and so on. This is a nice simple one where our constant c sub n is 1 throughout. However, c sub n could vary as well. So you could have a constant that is changing, just like any other series we've dealt with, but then our x power is also changing based on n in some way. So, basically, if you notice, this looks like a polynomial, except for this polynomial goes on forever. Okay, so a power series is a series of the form n equals 0 to infinity. Notice we're starting at 0 now. That isn't to say that we can't start at other numbers, just like we've seen in previous series, but we often allow for 0 because sometimes our power series, many times our power series actually start at a constant and then an x squared, so on, much like our normal polynomial concepts. Okay. Now, also, this could be like x to the n plus 1, x to the n minus 1, whatever. Again, it's not restricted to just n's, but this is our general form, where x is a variable, just like normal. C sub n's are constants, and they're called the coefficients of the series. And again, those constants can be changing. They could be a constant on each one, like the previous one, 1, 1, 1, 1, but they could be changing via like a geometric series or whatever. Okay. For each number that we substitute for x, the series is a series of constants. So basically, if we plug in like x equals 1 into a power series, then we get a series of constant numbers. And we can use that to test for convergence or divergence if we need. In fact, we will be doing that. We'll be plugging in values for x to find out whether it converges or diverges at those points. But the big thing here is that power series may converge for some values of x, and they may diverge for other values of x. Sometimes the only value for x that they converge would be 0, so then, it'd just be a 0. Other times it could be all real numbers in which it converges. The thing to keep in mind is that x is some value that is a real number, and so it's an actual number. It's not like some concept like infinity or something like that. X will be a constant of some sort if we plug in something for it. Okay. So, the sum of the power series is a function whose domain is the set of all x values for which the series converges. Okay. Now, a few things to note is that power series are things that we see to describe other functions. So like sine x as a power series. Okay. They're more specific things. Let's see. But we can write here, if we look here, I'm just pulling up generic. So sine x is equal to 0 plus 1x plus 0x squared plus negative 1 over 3 factorial x cubed. Basically, it's this. So this thing here, sine of x, is itself this power series. So we use these power series in higher level math really commonly. It's like a pretty normal thing to see. It's actually got its own special name, Taylor's formula, whatever. But the big thing here is that even things that we've dealt with that we think, oh, those are really normal and not weird, sine, can be described as a power series. Anyway, so it's just one of those things that you'll see them in higher level math and whatnot. Okay. So f of x resembles a polynomial that has infinitely many terms, again. Okay. A power series is a series in which every term is a power function. That is, again, a power function being a function of x to some power. We also have these things that are called trigonometric series. we're not going to really talk about them, but there are series whose terms are trig functions, obviously. Not to be confused with what I just got done showing you, the power series that describes what sine of x is, but considering we can describe sine of x as a power series, it's no surprise that we can also write trig series as well. Anyway, if we're talking about a more general form now, so here this is again the same thing, but now we're using this x minus a to the n. So again, a series of the form c sub n of x minus a to the n is equal to c sub naught plus c sub 1 times x minus a squared, and so on and so forth, is called a power series in x minus a, or a power series centered at, or a power series about a. So essentially the reason why we're writing this a here is that this power series is centered at a essentially tells us where it converges, centered on some interval centered on this point a. Now, one thing to note is that when x equals a, x minus a is 0, and we end up with terms of 0 for all n greater than or equal to 1, and so the power series will always converge when they're equal because it's 0. But basically, to determine the values of x for which a power series converge, what we're going to use is we're going to talk about the ratio or root test. Generally speaking, it's the ratio test. It's pretty uncommon to use the root test, but we can also use the root test to do that. It's just you see the ratio test so much more commonly. Okay. So let's take a look at a theorem first of all. So for a power series, there's only 3 possibilities that can happen. The series converges only when x equals a. That is, when you have 0 here. That's one possibility, because basically it will always converge in that case. The series converges for all x's. Basically, what we say there is that the series converges for x equal to all real numbers or whatever. And the other one, which is kind of the most common, is going to be, for us in a practical sense, what we're often running into is that there is some positive number r, which we refer to as the radius of convergence, such that the series converges if the absolute value of x minus a is less than our radius of convergence, and it diverges when x minus a's absolute value is greater than r, or the radius of convergence. The radius of convergence is said to be 0 when it converges only when x equals a, and it is said to be infinity when the series converges for all x's. Basically, the idea is if we had some interval in which it converged, let's say x converges between like 5 and, I don't know, 3 or something like that. Okay? Well, then let's think about this. This is from 3 to 5, which has a distance of 2. Our radius of convergence would be 1. That's basically what this thing is saying here. Now, you'll also see this just by the fact of if we would end up to get something like this, if we kind of go back in time a little bit. Essentially, this would probably be x's, it'd be like something like x minus 4 is less than 1, which is greater than negative 1. And so our radius here, absolute value x minus 4, would be less than 1. We can see the radius would be 1 here. Again, this is our radius of convergence, but if we solve for it, we'd add 4 to both sides, or all sides, I suppose, and you'd get 3 is less than x, which is less than 5. But again, the idea here is this radius of convergence is literally just describing, you know, if we have some center point, in this case, our center point, okay, 4, it's centered at 4, our interval is centered at 4, and its radius is 1, so it goes to the right one and to the left one. That's literally what these things are saying, and so they have some, you know, they make sense as far as what their name is and their naming convention. Okay, anyway. So when x is an endpoint of the interval, that is when x equals a plus or minus r, or basically going back to our example here, we know that if we can show that it like converges here between 3 and 5, the problem is that the root test and the ratio test tell us absolutely nothing about the endpoints, because basically, going back to what we were just doing here, is that the idea, if you remember, of the root test is we divide n plus 1 by the a sub n plus 1 over a sub n plus a sub n, and we take the absolute value, and it's less than 1. That's why something like this would be less than 1 here. But it doesn't tell us anything about it when it's like equal to 1. So we know when it's less than 1, it converges. When it's greater than 1, it diverges. And when it's equal to 1, we don't know whether it converges or diverges. So basically, that happens on our intervals. So we could show that 3 and 5, 3 to 5, it converges. But we don't know if we need brackets at 3 or parentheses at 3, or maybe brackets at 5 or parentheses at 5. We just don't know that based on the ratio test. So what we end up doing is we plug in the endpoints, 3 and 5, in for x, turn it into this normal series that we then test for convergence. So the only thing that makes a power series different than what we've been doing is that we have x's. But the second you plug a value in for x, the x's drop off. It's now a constant, and so we're just dealing with a regular series that we need to do one of our mini tests for. Well, mini tests. If it's a alternating series, then maybe alternating series test. If it's, maybe we'll do like a comparison test or something like that. Okay, so basically, that's what we do for those endpoints. That's the idea. So again, in general, the ratio test, or occasionally the root test, should be used to determine the radius of convergence R. The ratio and root tests always fail when x is an endpoint of the interval of convergence, so the endpoints must be checked with some other test. That's what we just got done saying. Okay, let's see this in action, because it's not that bad. Promise. I mean, no worse than the other ones, sort of. All right, we're doing algebra, though, so, a bit of algebra. Not too bad, though. We follow a pretty similar thing. So basically, if you remember, the root test and the ratio test, but in this case we're going to use the ratio test because in general we're using the ratio test. If we look here, not everything is raised to the power of n, so I know we're not going to use the root test. We're going to do a ratio test. So the limit as n approaches infinity of a sub n plus 1 over a sub n converges when it's less than 1. Okay? So we're going to use that knowledge and find out for what values of x this would be true. So let's take a look at this. That is to say, we're going to take x to the n plus 1 over n plus 1, and we're going to divide it by x to the n over n. We're going to take the absolute value, it's less than 1, and the limit as n approaches infinity. Okay. So one of the things to be aware of is anytime I have this something to a power, I actually don't even, if I know I'm going to be canceling these things out with the ratio test, I actually don't even write this. I actually start off by saying x to the n times x. That's what this thing is. Because I know this x to the n will cancel out, so anyway. And this is going to be times n over x to the n. All right, we're going to take the limit as n approaches infinity, and we're going to say is less than 1. Okay. Now, in the future, I'm also not going to be writing this until I actually need them, but for now, we won't be lazy on the first one at least. X to the n's cancel, and we end up with the absolute value of xn over n plus 1, the limit as n approaches infinity. So now we're going to look at, okay, well, at infinity, what happens? Well, basically, this is x to the n over n at infinity, which is less than 1, obviously. These n's will cancel, and so we end up with the absolute value of x is less than 1. So we are now in our form. This right here is our r, our radius of convergence. So r equals 1. So we know basically our radius is up 1 and down 1 from wherever we're centered. Hey, where are we centered at? 0. Because if you think plus a or minus a, whatever, this thing here is our a, but our a is obviously not visible. That's because it's 0. So basically a equals 0. So if you think about it, if it's centered on 0 and it's up 1 and down 1, well, clearly that's -1 to 1. But we can see that doing just normal algebra and not requiring any real thought. How do we solve for an absolute value? We have x is less than 1, and it's also greater than -1. That's how we do it. So basically, we drop it. It's x is less than 1, and then we write x is, and we flip this sign greater than -1. So we flip this sign and write this as a negative. So I just rewrote it here as a compound inequality. Okay, so obviously x is between -1 and 1. Well, there we go. This is our interval that we know for sure will converge. But now we need to test the endpoints. So let's say when x equals -1, what do we have in our sequence? So let's go back up to our sequence. So x to the n over n. So our sequence is x to the n over n. Okay? So when x equals -1, we have -1 to the n over n. And we need to know, does this, as n equals 1 to infinity, does this thing converge? Notice, like I said, sometimes you have 1s still, sometimes you have 0s, it just depends. Okay, so here, this is an alternating series. So based on that fact, all we have to do for the alternating series test is go, all right, well, if we can show that 1 over n converges to 0, okay, as the limit as n approaches infinity, and as n goes to infinity, this does go to 0, then that checks out. Then we need to show that 1 over r, so basically we have to show a sub n plus 1 is greater than a sub n for all n, or at least all n after a certain point, but whatever. So let's go ahead and take a look at a sub n plus 1 would be a 1 over n plus 1, and we have to show that this is greater than 1 over n. It is. I'm sorry. I meant less than. I wrote it in the wrong order. Sorry. So, less than. There we go. That's better. Okay, we have to show that a sub n plus 1 is less than a sub n for all values of n. And 1 over n plus 1 compared to 1 over n. We have n plus 1 and n. This one will always be a bigger denominator, so it's always going to be a smaller value, so that checks. So, -1 converges. When x is -1, it converges via the alternating series test. So, it includes -1. All right, now let's try it for 1. So when it's 1, our series looks like this, n equals 1 to the infinities of 1 over n. Well, this right here is a p-series, where n is 1. This is harmonic series, it diverges. So, because this diverges, 1 is not included in our interval. So, we would say then that this is our interval of convergence. This is our radius of convergence. And we can also note that this is the where our interval of convergence is centered on. It's centered on 0. Okay, so we know then that this series will converge as long as x is between -1 and 1, including -1, but not including 1. All right, let's take a look at another one. Find the radius of convergence and interval of convergence of this thing, square root n x to the n from 1 to infinity. Okay, so we're going to jump into the same thing. Again, this is the limit as n approaches infinity of absolute value a sub n plus 1 over a sub n. And we have to show for what values of x this will be less than 1. That's what we want to show. Okay, so again, I'm just going to jump into x to the n plus 1 can be written as x to the n times x to the 1 over the square root of n. And we're dividing by this thing. Oh, not over. Okay, we'll try that again. Square root n plus 1 x to the n plus 1. Okay, I'm not going to be lazy. I'm going to show it. I was going to be lazy, but since I'm rewriting this anyway. Okay, this is all over the square root of n, x to the n. Okay, that's our a sub n plus 1. Here's our a sub n. All right, now again, in the future though, I'm going to stop writing this, and I'm just going to write it as what it is in our practical sense, x to the n times x over the square root of n x to the n. Okay, x to the n's cancel. And again, this is all within an absolute value and all that jazz. Okay, and we're going to take the limit as n approaches infinity of this thing. So the limit as n approaches infinity of the square root of x square root n plus 1 over square root n. So as n goes to the infinities, the only terms that matter are going to be our n values here, that is square root x to the n. The plus 1 is meaningless, so it's basically this, over square root n. Those will cancel, and we get the absolute value of x is less than 1 again. So, again, our a here would be 0. Our r would be 1, so our radius of convergence, and our center point here is at 0. So clearly it's from -1 to 1, but just in case, we would solve this like normal. It would be x is less than 1, and it's also greater than -1. So that is between -1 and 1. So again, same thing. We now have this interval, and now we need to show whether the endpoints are included. So we're going to go back to our series here and plug it in. So the series is n equals 1 to infinity of square root n to the -1 to the n. So when x is -1, we're plugging in -1 here for x. This is an alternating series, and so in order to show that it converges, we need to show that the square root of n goes to 0 as n goes to infinity. So as n goes to infinity, the square root of infinity is infinity. Infinity does not go to 0, so it diverges by the alternating series test. So parentheses at -1. All right, we're going to check 1 now. So we have the series here, n equals 1 to infinity of square root n to the times 1 to the n. Now 1 to the n is just 1, so we don't really need it. So we need to show that square root n converges or diverges. Now if you think about this, this is n to the 1/2, which we could also write as 1 over n to the -1/2. This is a p series where our power is less than 1, diverges. All right, so it's not including either of our endpoints. So again, our interval of convergence, our radius of convergence, and our center point if we want it. Let's take a look at another one. Find the radius of convergence and interval of convergence of this thing. We have x to the n over n factorial. Again, they're not raised to the power of n, just this one is, so I'm not using root test. As I mentioned, the root test does get used, but so rarely. And anytime I see a factorial, I'm definitely thinking ratio test anyway. Okay, so again, it's the same thing. The limit as n approaches infinity of a sub n plus 1 over a sub n, and show that when that's less than 1. Okay, so a sub n plus 1 will be x to the n plus 1, which I'm going to write as x to the n times x to the 1, right? That's n plus 1, over n plus 1 factorial, but I'm going to go ahead and nip this one in the bud as well. N factorial can be written as n plus 1 times n factorial. So again, to be lazy, I'm still writing this out, so don't ask me why I'm trying to be lazy when I still end up having to write this out anyway. But I just want to point out that basically this is our a sub n plus 1. It's x to the n plus 1 over n plus 1 factorial, but both of these can be simplified a little bit to make canceling out easier. So that is, this can be written as x to the n times x, and n plus 1 factorial can be written as n plus 1 times n factorial. And that's just one of those things that, I mean, you should recognize when I have an n factorial that I'm going to end up having to cancel out. I need to get an n factorial out of this n plus 1 factorial. Stuff like that. Anyway, it's divided by this thing, so that's times the reciprocal, n factorial over x to the n. So notice again, I basically wrote it in this form to prepare myself to cancel things out. I need an x to the n, that's there, it's canceled. N factorial, canceled. So we're taking the limit as n approaches infinity of x over n plus 1, and we want to show when is this less than 1. Well, at infinite, we have the absolute value of x over infinity, which is less than 1. So which values will this lead to being less than 1? Well, all values of x. If I plug a value in for x, it will be a constant over an infinity, and thus it will be 0. When is 0 less than 1? Always. So here, our interval of convergence is from negative infinity to infinity, and our radius of convergence is infinity. So again, in this case, all x's will lead to this. So when x is 1, well, that would be 0. When x is a million, it's 0, and so on and so forth. Okay. Let's take a look at another one. Find the radius of convergence and interval convergence of this thing here. We have x to the n over n 3 to the n. Okay, so first things first, we're going to have our x to the n plus 1. Again, this is a to the n for both of these, but this isn't, so I'm not going to use the root test. I'm still using ratio test. X to the n plus 1 over n plus 1 times 3 to the n plus 1. I said I was going to be lazy, but I've just decided I really shouldn't be lazy. All right, so really, this is our n plus 1. So a sub n plus 1. So really, this is going to be x to the n times x over n plus 1 times 3 to the n times 3. And we're going to say times, because it's divided by this thing, so it's times the reciprocal, n, 3 to the n, over x to the n. So that's what we're doing. We're taking the absolute value, limit as n goes to infinity, etc. Okay, so x to the n cancels. N does not cancel. 3 to the n, though, does. Okay. So we get the limit as n approaches infinity of nx over 3 times n plus 1. All right? And we need to show when is this less than 1. Okay, so let's clean this up just a little bit. At the infinities, on top, as n approaches infinity, the top will obviously still be nx. On the bottom, only this n will matter. So it will be 3 times n. I mean, really, we could call this 3 times n plus 3 if we want to distribute it first. And it will show the same thing. At the infinites, only this n and the 3 that's being multiplied will matter. So that is nx over 3n will be less than 1. And obviously, these would cancel. And we get x over 3 is less than 1. Okay, so this right here is our radius of convergence again. Radius is 1. Okay. All right, so we're going to solve this thing. That would be x over 3 is less than 1, which is greater than negative 1. Multiplying both sides by 3, negative 3 is less than x, which is less than 3. Okay, so normally, when we have this thing, we would say like our radius is 1. But if you notice, what is actually our radius? Our radius isn't 1. It's going to be 3. So our radius of convergence here is 3. So really, this only works, this thing as r is here, when it's just an x, not like an x divided by something, x times something. So that's why it's important to recognize what our radius kind of is that like our radius is, all right, well, we're centered somewhere, and we go out 3 to the right and down 3 to the left. That's a radius, okay? And so that's just something to be aware of, is that students will often, and that's why I showed this one, students will often go, radius is 1, right? Because it's always that thing. But no, not always. So it's something to keep in mind. But our center here, that's plus 0. So it is still centered on 0. So a is still 0 here if we want to talk about the center point. So it's centered there. Okay, so we know from negative 3 to 3 it works, but we don't know if it includes negative 3 or 3. So now we need to try them out. So we're going to go back up to this thing and do it for negative 3. So let me rewrite that this sum as n equals 1 to infinity. I think it was 1. Yeah, x to the n, n 3 to the n. X to the n, n 3 to the n. Okay, so what we're going to do here is we're going to plug in negative 3 first. So that would be negative 3 to the n, which, if you think about it, we can rewrite this by pulling that negative out as an alternating series. it would be this thing times 3 to the n over n 3 to the n. Okay. So basically, we're pulling that negative out just to make our lives a lot better as far as it's an alternating series, and now we know how to deal with it. This is our b to the n, and also notice 3 to the n and 3 to the n would cancel, so we actually end up with negative 1 to the n over n. So this is an alternating series. We are going to do the alternating series test. We have to show that the limit as n approaches infinity is 0. So that is 1 over n. So this does, in fact, go to 0. So that's first check. The next check is that we need to make sure that a sub n plus 1 is less than this time, actually, a sub n for all n. So that is to say 1 over n plus 1 is less than 1 over n. So that checks out as well. So because, again, this is the harmonic series, but it's the alternating harmonic series, and we know the alternating harmonic series converges. We've seen that many times in the past. So it checks out. It converges via the alternating series test, so negative 3 is included here. Okay, now we're going to try out for 3. So we're going to plug 3 into this. We get 3 to the n over n 3 to the n, which would cancel to be 1 over n. This is not an alternating. This is just harmonic series. It diverges. It's the harmonic series. It diverges. It's a p series. The power is 1, so it doesn't include 3. So this would be our interval of convergence. Okay, let's try another one. Find the radius of convergence and interval convergence on this thing. The sum n equals 0 to infinity of n factorial x to the n. Okay, so again, we're thinking, all right, well, a sub n plus 1 is equal to n plus 1 factorial x to the n plus 1, which again, I'm going to just go ahead and write this as n plus 1 times n factorial times x to the n times x. That's what this thing is. I'm splitting it up because I know I'm going to be dividing it by n factorial x to the n. So again, this is all over our a sub n. Okay, so if you notice, n factorials are gone, x to the n's are gone, and we want to show the limit as n approaches infinity of n plus 1 absolute value times x will be less than 1. Okay, when n goes to infinity, we end up with infinity times x. Now, the only time infinity times a constant will ever be less than 1, i.e. not infinity, is when x equals 0. So x equals 0 is the only time. So that is to say our radius of convergence is 0. And it only converges when x equals 0. That's it. So it pretty much doesn't converge. The only time it would converge is if x equals 0. And yeah, which is pretty meaningless if you think about it. That would just be because when x is 0, this would be a 0 here in every term. So when n is 0, you'd have 0 factorial would be 1 plus 0 plus 0 plus 0 plus 0. So it's a pretty meaningless series at that stage. So we know then that this power series basically diverges everywhere except for in this one kind of like trivial concept. All right, let's take a look at another one. Find the radius of convergence and interval of convergence of this thing, x minus 2 to the n over n squared plus 1 when n equals 0 to infinity. Okay, same thing as before. We're going to do our a sub n plus 1 over a sub n. So that is to say x minus 2 to the n plus 1 over n plus 1 squared plus 1 kind of thing. And that's all over our x minus 2 to the n over n squared plus 1. Okay, so if we think about this, on top we have x minus 2 to the n times x minus 2 over, I'm going to go ahead and distribute this out. That would be n squared plus 2n plus 1 is going to give us plus 2 here. And then this is going to be times n squared plus 1 over x minus 2 to the n. Okay, x minus 2 to the n's cancel, and we get the limit as n approaches infinity of x minus 2 times n squared plus 1 over n squared plus 2n plus 2. All right, and this is absolute value. Okay, so if we think about this thing, at the infinites, only this n squared would matter here, not this 1. We could also distribute this or foil this if we want. It doesn't really matter if we foil it ahead of time or not. It might avoid some kind of confusions for you, though. If you're worried that, oh, does that mean we're just dropping this 1? Do we drop this 2 as well? What about the x? Well, we're just dropping this 1, but I'll show you why. If we foil this, we get x n squared plus x minus 2n squared plus, or excuse me, minus 2. Okay, now at the infinites, this doesn't matter and this doesn't matter, so we only have xn squared minus 2n squared, which is, if we factor out the n squared times x minus 2. So again, only that 1 dropped off at the infinites. And at the infinites, the only one that matters here is the highest power of n here. So these n squareds drop, and we get x minus 2 is less than 1 here. Okay, so in this case here, this thing is our a. So negative 2 is our a. That's our center point. Our radius here, r, is 1. We may have to think about it later, but I always just start there at least. R is 1. But this is in our standard form, so it should be. So basically, if our radius is like 1 and we're centered at negative 2, that would mean that it goes like down to negative 3 and up to negative 1. But let's see, because that's not going to be the case here. I forgot, it's not centered at negative 2. It's the opposite sign. It's centered at 2. That's better. So if we start at 2, we're centered at 2 here. Radius of 1, it goes up to 3 and down to 1. That's more believable based on this math here. So that's why I don't get too caught up in like any kind of memorization or anything. It's just I like to use logic to think about it as well. Sometimes my logic screws up. Well, the logic usually doesn't screw up. It's usually my memory where I go, oh yeah, a is this thing. Well, no, actually a isn't negative 2, it's 2. So it's just something to be aware of, because obviously I don't remember everything. And so that's why I like to apply logic to the stuff. And so when I know what it is that I'm dealing with, then I can apply that logic and make sure that I'm remembering things right or doing things right or whatever. Okay, so anyway, we have our x minus 2 is less than 1. It's also greater than negative 1. So we're going to add 2 to both sides, and we get 1 is less than x, which is less than 3. So exactly as we'd expect once we applied correct logic. It's centered at 2 with a radius of 1, so it's up to 3 and down to 1. So that is, our interval is from 1 to 3. But again, we need to check. Does it include 1? Does it include 3? Okay, so we're going to go back to our series here and plug in 1 and 3 into them. All right, this was x minus 2 to the n. X minus 2 to the n over n squared plus 1. Let's double check though. Yes. Okay. N equals 0 to infinity. All right, so we're going to plug in 1. When x is 1, we end up with 1 minus 2, which is negative 1 to the n over n squared plus 1. And we have to show that this thing would converge. It's an alternating series, so I'm going to try the alternating series test. So that is to say, I need to show that the limit as n approaches infinity of 1 over n squared plus 1 goes to 0. It does. Okay, then I need to show a sub n plus 1 is less than a sub n for all n. That is 1 over n plus 1 squared plus 1 is less than 1 over n plus n squared plus 1. And no matter what, if we increase this by 1 before we square it, this would be a bigger number on the bottom than this one. So this is also clearly less than, so that checks out. So 1 converges by the alternating series test. And now we'll check 3. So 3 minus 2 is 1. So we end up with 1 to the n over n squared plus 1. Now, 1 to the n is just 1, so I don't really need it. So we have 1 over n squared plus 1. Okay, so I want to show that this converges. Now, I recognize that that's pretty close to a p-series. So we can see that 1 over n squared plus 1 is clearly less than 1 over n squared. This is our p-series. This p-series here converges. And since this is less than it, it also converges. So it converges by direct comparison. So this is also included. This is our interval of convergence. This is our radius of convergence. This is our center point. Okay, so that is our power series. And again, it's not too bad once we recognize what we're doing and kind of like follow the same basic procedures we've been doing. The root and ratio tests are kind of some of the easier tests that we have. Well, at least personally, I find them easier just because they're some basic algebra. And so they end up essentially being pretty straightforward. Power series, when I was a student, was very complicated. I didn't understand it because I never learned these power series. But in hindsight, when I started teaching it, it's like, oh wow, if only somebody had explained that to me. So again, if you go further in math, power series are definitely something you see a lot of. And it would be important for you to know that. Anyway, thanks for watching.